Yes, thank you. Good morning, everyone. Thank you for attending the session. So I'm going to talk about the intersection between data availability sampling and sharded mempools. A little bit of context. First, I'm going to talk about what is the motivations for this research and what is the state of the art today, what we have today. And I'm also going to explain a little bit what we expect to have tomorrow. By tomorrow, I mean in the next fork, so Fusaka. And then I'm going to talk about what I'm proposing, what we are proposing as researchers to the next fork, so Amsterdam, and how this can help Ethereum scale. So yes, all this research started more or less in 2018 when Ethereum decided that we needed to scale way beyond where we were at the time, but we wanted to do it in a way that it was that it kept Ethereum decentralized and secure. Okay, so this is like the quite famous trilemma. And it's important because to keep this in mind, because scaling is rather easy if you don't care about decentralization. So you can just put a lot of data centers to work, and that works fine. But then you won't have the decentralization, which is, I think, the main thing that makes Ethereum. So at the time, there was a proposal in 2018. On the left side of the slide, you see the sharding proposal that was evaluated at that time. That was later changed by a rollup-centric approach, which is the screenshot that you see on the right. And so the idea is that rollups are going to help us scale, but that also has a cost because rollups need a space. They need a space to put their proofs, their data, and so that has to come into the L1, into the main Ethereum chain. But then the question was where we put this. So in DNEP, we had an option before, which is cold data. Cold data is something that you can use in Ethereum to put your data there. Now, this has some problems. One of the problems is that when you store something on cold data, that is going to live there forever. So you can not remove it. It's going to be there always. The second problem is that this has limited space. More or less, all the blocks that you see in the Ethereum chain, at least at the time before DNEP, were about 100 kilobytes in size. And you could actually put a lot of data in cold data and make the blocks really big, like up to 2 megabytes. We have seen blocks, organic blocks. But yeah, that's still quite limited. And the other problem is that this is kind of an expensive storage. Okay, so to solve that problem, we created Tinder. Blobs. Which blobs are like the Tinder of Ethereum, right? This solves several problems. So if you don't like those long-term commitments, you can put your data in blobs, and they are going to disappear in 18 days. So you don't have to look at them never again, and that's it. So that's easy. It's also offer more space, because in blobs you can store up to tens of megabytes, and hopefully even hundreds of megabytes in the future. And that also solved the third problem, which was that cold data was expensive, because blobs offer an independent market. Okay, so that was, like the whole idea of having blobs is that we can solve these three problems using this ephemeral storage that where you can put rollups can put all their proofs and all their data, and it's ephemeral. So in 18 days is gone, but that is enough to guarantee the security of the rollups. So that's all good. That worked well. And so we have had blobs since DNEP, so that's over a year ago. And this is a dashboard that shows the distribution of how many blobs per block we have seen. We were seeing, at least in the chain, at least at the time of DEF CON in Bangkok last year. That's where these snapshots were taken. And And yeah, so you see more or less the distribution. We also see on the right side the average propagation time of the blobs on the network. And this is important because, for those that were here for the previous talk, we transmit these messages over the peer-to-peer network through Gossip Sub. And Gossip Sub has some limitations, in particular for large messages like blobs. And so it was important for us to keep track of how much time does it take to propagate a blob over the entire peer-to-peer network. And as you can see, it takes about 2 seconds, which is fine because slots are 12 seconds. And if you have your data in 2 seconds, then you can validate the block and keep working and moving forward. So that's all good. It has been working well for over a year, and that's great. Now, today we have Pectra, and in Pectra we increase the number of blobs because we want to scale. We are trying to do it gradually, which is reasonable. Today we have moved to a target of 6 blobs per block and a maximum of 9. So the difference, what you see here in this figure is in blue you see how many blobs per block will you see before Pectra, so that's when the maximum was 6 and the target was 3. And on yellow you see what is the distribution of blobs per block after Pectra. So 10 days before Pectra and 10 days after Pectra. And now you see the presence of blocks with up to 9 blobs. Okay, so we gain more space, which is help for scaling because now we have more space where rollups can put their data. And that means the rollups themselves have more throughput. And then if you aggregate all the throughput of all the layer 2s plus Ethereum, you have much more throughput overall, the entire Ethereum ecosystem. Now, we don't want to stay at 9, of course. We want to scale beyond 40, 50 blobs. Hopefully one day we can reach 100 or perhaps 200 blobs per block. And that's what I'm going to talk about today. So what are the plans for tomorrow, or Fulu Osaka? Is what we call PRDAS. So for PRDAS, so we have been working on PRDAS for a couple of years already. The idea of PRDAS is that not everyone in the network has to custody all the blob data all the time. That's pretty much the main idea. Basically, what we do is data sharding. Is you are a node in network, you only have to custody this part of the data. Another node will have only part of the data, and another node will have another part of the data. But we all together as a network have all the data. Now, this is a little bit complex because when you only have a part of the data, what does it make you trust, or what that makes you believe that actually we as a network, we have the entirety of the data? And this is a really hard problem to solve in computer science, and that's what we came up with data availability sampling. Sampling means that you have to ask your neighbors some parts of the data they are supposed to have, and if they answer yes, then you have a very, very high probability that actually we as a network have the entirety of the data. So in PRDAS, what we do is that blobs are disseminated over the dev peer-to-peer network. So this is execution layer. This is the first part. The execution layer nodes downloads the blobs by pooling. They extend them with something that we call erasure coding, which in this context is not going to be relevant. I'm not going to talk much about that. But yeah, they are extended so that we have some redundancy there. And then the consensus layer nodes verify that the blob is available, and they divide this. So what you see in this figure is every blue rectangle is a blob, okay? And the columns that you see, the green columns that you see, is what this particular node has to custody. To custody means he needs to storage these 2 columns in his hard drive for the next 18 days. And other nodes will do the same with other columns. And we all together have the totality of the blue rectangles. Okay? This is basically data sharding. This is what we call PRDAS. And this reduces the amount of storage that nodes have to consume and also the bandwidth they have to consume at the consensus layer, because they, instead of downloading the entirety of the blob data, now they only focus on a number of columns. So in this picture, I put 2 columns, but in reality, the minimum is 4, okay? 4 out of 28 columns is what you are supposed to download as an Ethereum node for PRDAS. That means for Fusaka. Okay, so this is what we expect to come, hopefully, in the last part of this year. This should come alive in Ethereum network. And so there is nothing really new about this. We have been working on this for several years. We wanted to have this in Pectra. We didn't manage. Hopefully, it's going to be in Fusaka. I think it's going to be in Fusaka. Now, what is the next step? Okay, and so this is what I want to present today. Is what is expected after Fusaka. So, as I mentioned before, we extend the nodes one-dimensionally with erasure coding. But the idea is that at some point, we are going to reach 256 blobs. So that's a total of 32 megabytes of space to put rollup data. But we also extend that vertically to have double two-dimensional erasure coding, right? And in contrast with PRDAS, now we don't have to custody only columns, but we also need to custody rows. So every node will have to custody a number of columns and a number of rows. So this is important for what I'm going to present later, that to understand that in the next iteration, we are going to need to custody also rows and not only columns. And this is important for reconstruction in the two erasure coding case, okay? So this is what we want to reach as an objective. Now, and this is what I propose. We have been working on this research, but what I'm present today here is blob pool sharding. So as I mentioned, the custody is already sharded at the consensus layer, but it doesn't really make sense to only shard at the consensus layer if at the execution layer, the nodes are actually downloading all the blobs in order to create blocks, right? So this is kind of a, you know, a little bit ridiculous that we focus so much on limiting the number of data that you custody at the consensus layer, if in the blob mempool of the execution layer, you are downloading all the blobs. So at the scale, we want to have so many blobs that this is not going to scale. So it's clear to us that at some point, we are going to have to shard this as well. Shard, what means? It means that not all the execution layer nodes will download all the blobs, but only part of them, okay? And still, we need to make sure that the mempool as a global system works well. So what we suggest here is to shard it through the, using the transaction hash of the type T transaction. So every blob is attached to a type 3 transaction. And what I propose here is that if the last 4 bits of the type 3 transaction hash match with your node ID, with the last 4 bits of your node ID, then you download that type 3 transaction and all the blobs that are attached to it. If it doesn't, like in the case of the second transaction that you see in the screen, then you don't need to download that transaction. Somebody else will do it, right? And in this way, basically what you are doing is dividing all the type 3 transactions, so all the blobs, you are dividing them in 16 different bins, and different nodes will take care of those different bins. Now, the network today has about 8,000 nodes in the Ethereum network. If we divide all the transactions in this way, pretty much every blob will live inside about 500 nodes, okay? So that's a lot of redundancy right there. That means every single type 3 transaction, every single blob that you submit to the mempool is going to exist in about 500 nodes, okay? So it's very redundant. So that's still very safe. But at the same time, you are only downloading, the nodes will be only downloading 1/16 of the total number of blobs, okay? So that's a great reduction so it's 94% reduction in the amount of bandwidth that you need to use for downloading blobs at the execution layer. So we could start implementing this today. Actually, we have started implementing this today. We have 2 work in progress in Geth and Red, and we are going to deploy these versions in some devnets next week. So this is already work in progress. And then the idea is that you will end up with a network in which different nodes with different node IDs will end up having different blobs in their mempools, but altogether we have the entirety of the blobs. We did some experiments as well. This is not a simulation. We took the real node ID of the 8,100 plus nodes in the Ethereum network, and we classified them in 16 different charts according to the real node ID. And this is the distribution that we observe. So it is a very homogeneous distribution. What you see is how many nodes will be located in each one of the charts. So again, you will see more or less 500 nodes in each chart, which is, again, very, very good in terms of redundancy. Now, we also looked at all the type 3 transactions. The type 3 transactions are the transactions that carry blobs in Ethereum. We look at all the transactions from Pectra until last week. So that was a total of over 250,000 transactions. These, again, are real transactions that we see on mainnet. This is not simulations. And we classify them in different charts according to their hash and the last 4 bits of their hash. And again, what we observe is a very homogeneous distribution in which you have about 16 transactions in each one of the bins here. So in each one of the charts, let's say that way. Now, one thing that one has to pay attention is that in a type 3 transaction, you can attach 1 blob, but also you can attach 7 blobs. Okay, so it's up to the rollup or the one that is submitting the transaction to decide how many blobs it wants to attach. So that could create some, disparity here in the homogeneity of the that I'm presenting here. So we also look at the blob, distribution, and this is what we observe. Again, so 250,000 plus transactions translate into about over 700,000 blobs, and this is the distribution that we saw in the 16 charts that we are proposing. So it's still a very homogeneous distribution. Now, somebody comment, yeah, but maybe it's because you are looking at the data for several weeks, and maybe that's what makes it homogeneous. Maybe if you look at the data for just one specific day, maybe you will see much larger disparities. So we plotted the data in this way as well, which is the same data that I presented just seconds ago, but it shows for every day what is the distribution of the charts. So the lowest part of the bin is the chart that had the minimum number of blobs, okay? And the max of each bin is one chart that had the maximum number of blobs. And what we want to see is that the bins in this figure should be very, very small. So the difference between the min and the max should be as small as possible, okay? If there are too large difference, like for example, the day 14 in the figure, that means that in that particular day, there was a large disparity in where the transactions were located in the charts. There was a chart that had many, many transactions and maybe another chart that didn't have many transactions, okay? But overall, you see here, and please not pay attention to the y-axis, that is kind of zoom. So that's why we see more or less these large bins. But overall, I think is a fairly good distribution. This is the same figure, but divided in 12 hours instead of 24 hours. And if you focus on shorter intervals, like 6 hours, this is more or less what you will see. And you see that there is kind of a line of about 400 blobs, right? And you see that the distribution across these 6 hours is not that high. So that's good. Now, we also looked at other way of sharding. Instead of using the hash of the transaction, we could use the transaction sender. That means who is sending the transaction. So in that case, you will end up, for example, with all the transactions from Base in one chart, all the transactions from Arbitrum in another chart, assuming that they use the same address. I mean, each one, they use always the same address. And the distribution we saw was this one, that basically is not homogeneous at all. So this is not great. And we also noticed that even if we hash the transaction sender, the distribution is not great. So this strategy, at the moment at least, doesn't seem to work very nicely. So the other thing that I want to propose is the partial column dissemination, in which instead of sending the entire column through gossip soap, you say just a partial column because you only have part of the blobs. And then when you merge those all together, you can reconstruct the entire column. And in that case, I think we can reach the 256 blobs that we were targeting. So just to finish, there is a bunch of options that we can add to this scheme that I don't want to get into the details because I don't have time right now, but we can discuss offline, or you can ask me in the questions. But overall, I think this is a good way to decrease the bandwidth consumption on the execution layer and to have a much more fair balance sharded mempool at the execution layer that also cooperates with the way data is going to be custody in the consensus layer. So that's all for my talk. Thank you very much.
Thank you, Leo. And there's also, again, there's the QR code at the top right corner for questions, and there's already a bunch of questions here. I'll start with the most upvoted one. Is there a potential denial of service vector if attackers decide to manufacture type 3 transactions that intentionally have the last 4 bits?
Yes, so you could find a way to mine transactions in the way that they are going to always land in a specific shard. That is one of the concerns that we have. However, if you are doing that and assuming the transaction is valid, you are at the risk of having to pay for those transactions. So in order, I mean, it doesn't really differ much of the status today. And the reason for that is that we are charting in a horizontal way, which means when you get the blob, you get the type 2 transaction and all the blobs, and you get everything to verify that is a valid transaction. And if it's a valid transaction, you can add it into a block. So that means you have to pay for this attack. And so it doesn't really change much into how to attack the mempool today. If it was a vertically sharded mempool, which is another proposal that I didn't mention, then there will be much easy attack vectors and easy ways to DOS the mempool.
Okay. And the next question is, does the blob mempool sharding have any impact on transaction inclusion latency?
Yes, that's a very good question as well. It does. And one of the concerns about this proposal is that you might end up in a scenario where you send a transaction and it ends up in a shard, and then you send the next transaction, and that ends in another shard. But the one that is the node that is looking at this shard cannot include this transaction until the other one that is included in the other shard. And if you don't have a complete vision of all the shards, that could end up in delay in some transactions. And this is a valid concern. We are working on it. Actually, one of the ideas of proposing to chart it through the transaction sender was exactly to avoid this scenario. Unfortunately, the distribution in that case is not very homogeneous, so then that leads to another problem. But yeah, it's a valid concern, and we are trying to look into it. That said, I think most of the builders today will anyway download all the charts, and most of the nodes in the network that are not interested on proposing blocks or producing blocks will be only downloading their respective charts. There is also a proposal to change the behavior of the mempool temporarily. So you only download your charge, but when you know that you have to propose a block in the next epoch, then you change your behavior, you download all the transactions, and then you propose your block, and then you go back to the normal behavior, which is only looking at one chart. So there are strategies there, but we have to look at the pros and the cons.
Okay. There's some additional questions, but we're a bit out of time. Okay. So let's give a round of applause. And for additional questions, you can catch him in the hallway. Thank you, Leo.
Thank you.